Hi, in this video we're gonna discuss another one of those divide and conquer sorting techniques called quick or pivot sort. This technique is similar to merge sort in the sense that we're going to divide the original collections of values in half and then proceed to sort each half. So it's a recursive method very similar to merge sort, in which we divide the collections in half as much as we can, and then we merge the values, and at the end the values in the collection should be sorted. The quick sort is also known as the pivot sort because we choose a value called the pivot, and that's the first step of the algorithm for this technique. Once we have chosen the pivot, then we're going to divide the collections into half, which we call partitions. A partition that contains all the values which are smaller than the pivot, and a second partition that contains all the values which are greater than the pivot. For example, in this diagram you see that this kind of cloud represents a large collection of values, and we pick a pivot, and the pivot has value 28. So what this technique, this sorting technique does is then to create two partitions. One partition where we move all the values in the original collection which are less than 28, and a second partition which contains all the values from the original collection which are greater than 28. When we finish that first step, then we have a pivot 28 and two partitions. So I could make the claim that right now the values are sorted with respect to 28. Why is that? Well, because I can claim that all the values in this partition are greater than 28, and all the values in this partition are less than 28, and of course in the middle I have 28. So with respect to 28, the entire collection of values should be sorted. But of course this is not what we want, right? What we want is to have all the values numerically in increasing order. So recursively, the algorithm for the quicksort technique, what it does is to take each partition and then divide it into two other new partitions. Of course, every time that we divide each partition, then we get, or we end up with a partition which is smaller in size. But now we repeat the entire process. So for this partition here, which contains values less than 28, we find a new pivot like 15. And for this partition which contains values greater than 28, we find a pivot which is 47. Notice that the value of 47 is greater than 28 and the value of 15 is less than 28. So now what do we do with this set of values? We create two partitions. Partitions of values which are less than 15, partitions of values which are greater than 15. This partition contains values which are greater than 47. This partition contains values which are greater than 47. So here, as you can see, I can claim now that the values in here are less than 15, are less than 28, and are less than 47. The values in this partition, I can claim, are between 28 and 47. The values in this partition are greater than 47. The values in this partition must be between 15 and 28. So as you can see, little by little, every time that we apply recursion, every time that we split the array, then we are placing the pivots in the correct positions. When this is sorted, the 28 will never move, the 15 will never move, and the 47 will never move. And I guarantee that these values here will be less than 15, these values here will be between 15 and 28, these values will be between 28 and 47, and these values will be greater than 47. So let's see how that works using numerical values. Let's assume that we're given a random collection of values like the ones that you see here, and I'm going to pick the first number as the pivot. I'll discuss later on how do we choose a pivot, but right now, for the sake of it, just pick randomly 29, which is the value in the first position. So what I have to do now is compare the remaining values with respect to 29, and I'm going to move to the front of the array all the values which are less than 29, and to the back of the array all the values which are greater than 29. And those are going to be my two partitions. So the first thing that I do is to, starting from the front of the array, from the left side, I'm going to search for the first value that is greater than the pivot. Okay, I'm going to search, starting from the left, for the first value that is greater than the pivot. So I compare 14, that's the first value, because I'm not comparing the pivot with itself. Well, 14 is less than 29, so that's not a good value. So I move to the next location and I find 37. And 37 is the first value that I found which is greater than the pivot. So at this point, I know that I need to move 37 to the back of the array because 37 is greater than 29. And what the technique does is to swap 37 with the last value in the array. So I'm going to swap 37 and 64, right? And that gives me 64 here and a 37 there. It's important to understand that the algorithm is keeping track of the indexes in the array that I'm using to start my searches. So right now, the algorithm knows that the next time that I start from the left, the front of the array to search, I'm going to start in the second position because that's where I found the first value, original value, that was greater than 29. So now, the recursion changes a little bit and it says, well, now instead of starting looking for the front of the array, I'm going to look from the back of the array. And in this case, I'm going to look for a value which is less than the pivot. So remember, we're sitting at here. So that's the first value compared with the pivot. 37 is greater than 29. And then 32 is also greater than 29. And the first value found that is less than the pivot is 25. So at this point, I know that I need to swap 25. Or 25 with which value? Oh, remember, we left from here, which is the third value in my array. So I'm going to swap this new value that I found starting from the back, 25 with 64. And once I do that, then 25 ends up here and 64 ends up there. And again, I'm keeping track using two separate indexes or of where I am. So I underline these two numbers indicating that right now I'm creating my partitions. And now I have a partition with two values, 14 and 25, which are less than 29. And I have a second partition, 32 and 37, which are greater than 29. And those are the two partitions similar to what I have on this diagram that I'm creating. Okay? So what happens next? Well, now I start again from the front and I search for the first value that is greater than the pivot. But remember that I know the indexes. So I know that I finish comparing here. So I'm going to start here searching for a value that is greater than the pivot, and I found 40. And again, I need to swap it with one value on the right, but remember, because this is the value that we found last time, I know that I need to swap these two. So the bottom line is that I need to swap 40 and 64. So I do that, right? And then realize that I have two partitions. One partition that has the values greater than the pivot, and that partition is to the back of the array, or those values are toward the back of the array. And then I have a second partition which contain values which are less than 29, and those are toward the front of the array. At this point, okay, the algorithm realizes that I was swapping two values that were adjacent to each other, 40 and 64. So the algorithm recognizes that, okay, there are no other values that need to be swapped at this point. The last step, and a very important step of the algorithm, is to move the pivot to the right position. Right now, the pivot is at the front, so what I need to do is to move 29 in between those two, and the algorithm will take care of that. So at this point, I can claim, again, that these values are sorted with respect to 29. The partition on the left has values which are less than 29. The partition on the right, values which are greater than 29, and that's exactly what the objective was. Of course, this is not completely sorted. I want all the values with respect to each other sorted. So the technique, what it's going to do is going to take this partition and do the same thing. In other words, determine a pivot and then create two partitions with values greater than or smaller than the pivot, move the pivot to the right position, and then this one, again, find a pivot and create two subdivisions. So it's going to be pretty much what I have indicated in this picture, okay? So eventually, the partitions are going to be so smaller that there will be one or two elements which are going to be already sorted, and then I have all the values in my array sorted as I want them. So it's a divide by two technique which uses the value of the pivot. So let's do some algorithm analysis of running time. So first one, and this is a recursive algorithm. All the divide and conquer sorting techniques, merge sort, and this one, quick sort, uses recursion. The second thing is, for analysis, we are comparing the elements on each partition, right? We're always searching for a value which is greater than the pivot or a value that is less than the pivot. So we need to do some sort of comparison. So, and the worst scenario is that we have to compare all the values. So it's impossible that the order of magnitude, the running time, will be greater than n, where n is the numbers of elements. Now, what do we do? Well, we need to create the partition. So similar to what we did with the technique in merge sort, we need to partition the array by basically dividing by 2. So we have what we call k partitions, and k partitions is equal to the log base of 2 of n. And that comes because if we have n elements, we need 2 to the k, where k is the numbers of partitions. And now we need to multiply those two, so n times log 2 give us a total running time of quicksort, which is n log base 2 of n. This happens to be the same as merge sort. So before we go into the worst scenario, let me do some comparison. If you remember, merge sort has the same running time, but one of the disadvantages of merge sort is that it requires lots of memory because we need to create subarrays and then merge them. One advantage of the quicksort is that moving the elements is in place. We don't need extra memory. They are being done within the array, so we don't need all but the original array. With regard to running time, the average is about the same. Merge sort is always the best scenario, the worst scenario is always the same. Now, we need to be careful with quicksort because there is a worst scenario case. What is the worst scenario case? The worst scenario case will be one in which we end up only with one partition. So let me go back to picking the pivot here. What if the value of the first element is 100 instead of 29, and we pick the pivot to be 100? Then all the other values in the array are less than the value of the pivot. So when I try to create two partitions, I only end up with one partition, the partition that has all the values less than the pivot, which in this case would be 100. That is a problem. So the worst scenario happens when, by chance, I only have one partition. And if I only have one partition, then I cannot divide the array using n divided by 2, but it has to be simply n. So n times n ends up with being n squared. And of course, as you already know, there's a huge difference between a running time of n squared and a running time of n log base 2 of n. So you could think as quicksort then as having a serious, very important disadvantage, which is the worst scenario case. In real life, quicksort is one of the sorts that is used most commonly on a daily basis. So how do we avoid the problem of the worst scenario? Well, we avoid the problem by being very smart about how we choose a pivot. So let's talk about that. Okay? So we could choose a pivot randomly. Okay, we could say, all right, look at the values that we have on our collection and then pick a random value. Or we could say, always pick the first value or always pick the last value. Those three techniques are not going to guarantee that we end up with two partitions. A commonly used technique which almost guarantees that we're going to have two partitions is called the median of three values method. This technique says, take a look at three values in your collection. Specifically, take a look at the value in the first location, the last location, and the middle location in your array. So in this case, we're looking at 29, 13, or 40 for that matter, doesn't matter, and the last one is 64. And then we calculate the median. And when we calculate the median of 29, 13, and 64, the median obviously is 29. So we choose 29 as the pivot, and that's what I did in this demo. So once you choose that value, you can move the value to the first position on the array, as I did, or you can move it to the last position of the array. It really doesn't matter. What the important thing is that by placing the chosen pivot on the first element or the last element, you are sort of moving it out of the way, and then you're left with the rest of the numbers to be sorted. So That explains why when I chose the pivot, I chose 29, because I knew that the median of the values would be 29, and then I'm left with the rest of the array to be partitioned and eventually sorted.